What if I told you that you could predict a machine's future? Not, the stock market or anything, but a complex system, just by looking at a map. Well, today, we're diving into root locus analysis, which is this absolutely brilliant tool that lets engineers do pretty much exactly that. It helps them make sure everything from a drone to a self-driving car stays perfectly on track.
You know, every single control systems engineer out there has to answer this one critical question. How do you design your system so you know for sure that it's going to work perfectly, without shaking or stalling out or just spiraling completely out of control?
A huge part of the answer comes down to tuning. And one of the most basic things you can tune is something called gain. You can just think of it like an amplifier knob. But it's this incredibly delicate balancing act. It's like walking a tightrope, really. So if you set that gain, that K value, way too low, the whole system just gets sluggish. It's lazy, it reacts super slowly, and just doesn't do its job very well. I mean, imagine a thermostat that takes an hour to actually change the room temperature. Yeah, not very useful, right? But on the flip side, if you crank that gain knob way up high, the system can totally overreact. It starts oscillating wildly. And this is where things get dangerous, where you hit instability. The system could literally shake itself to pieces or just go haywire. So the goal is to find that just right spot, that sweet spot. But how in the world do you find it without just endless, expensive trial and error? Well, it turns out there's a map. And this is where the absolute genius of a guy named W.R. Evans comes into the picture. He developed a graphical method that's basically a treasure map for system behavior. It's called the Root Locus method. Okay, I know. The official definition can look a little intimidating, but the idea behind it is just brilliant. So every system has this core mathematical identity, its characteristic equation. The roots of that equation basically define how the system behaves. Is it fast, slow, stable? The root locus method just draws a picture of how that behavior changes as we turn that gain knob K all the way from 0 up to infinity. So let's just cut to the chase. The root locus is a visual map, a map that shows every single path the system's behavior can possibly take. So instead of guessing, we can literally see exactly what's going to happen at any gain setting. It's amazing. Now, to read any map, you need to know the landmarks, right? Well, in control systems, our landmarks are called poles and zeros. Think of it this way. Poles, we mark those with little crosses. They're the system's natural default settings. They're the starting points of our journey on the map, right where the system is when the gain is at 0. Zeros, those are the circles. They're like magnets. They're the destinations that the system's behavior gets pulled toward as we crank that gain all the way up. And here's the really cool part. This map isn't just some random scribble. The paths, or the loci, they follow a very specific set of rules, all based on where those poles and zeros are. Let's just look at a couple of the simple ones. Okay, so every single path has to start at a pole, and it has to end at a 0. Simple enough. Then there's this kind of funky rule for the horizontal line, the real axis. A spot is only on a path if it has an odd number of poles and zeros to its right. And because of the math under the hood, the whole plot is always a perfect mirror image of itself. All right, let's make this real with a classic textbook example. Imagine a system with 3 poles. 1 at 0, 1 at -1, and 1 at -2, and no regular zeros. Just from our rules, we already know that 3 paths have to start at these 3 spots. So, we have our map. We've drawn it out. Now for the payoff. How do we actually use this thing to find that perfect, stable setting for our gain? This is it. This is the single most important rule for reading our map. See that vertical line right down the middle? That's the imaginary axis, and it is the ultimate boundary. If all the paths, all the routes, stay on the left-hand side, your system is stable. It's happy. The very second, even one of them crosses over to the right side, it's unstable. So if we look at our plot, when our gain K is low, anything below a value of 6, all 3 of our paths are safely tucked away in that stable left half plane. The system is well behaved, everything's good. But as we start turning up that gain knob, the system's roots start to move. They travel along these paths that we've already drawn, heading out from the poles and getting closer and closer and closer to that stability boundary. And then we hit the tipping point.
At a very specific gain value, k equals 6, two of our paths cross that critical vertical line. The instant they cross over, our nice, stable system becomes unstable. It breaks into these uncontrolled oscillations. And that's the power of the map. It doesn't just tell us if it will fail, it tells us exactly when.
So when you put it all together, the root locus map is so much more than a graph. It's like a crystal ball for engineers. It gives you this complete visual prediction of how a system's going to behave. It lets a designer confidently pick a setting that gives them really high performance while staying a safe distance from the edge of chaos. It's just an invaluable tool. And that really just leaves us with a final thought, doesn't it? It's kind of amazing that a graphical technique, basically a simple drawing that follows a few clear rules, can give us such a deep, immediate understanding of a system's really complex mathematical behavior. It is just a perfect example of the power of visual thinking in engineering.